Good day, ladies and gentlemen. Glory Valentino Moore is my name. I am a PhD candidate, Department of and Structural Integrity from the Center for Research in Advanced Material Science, CMAP. I thank the organizers of the 16th CSM's conference. As part of my research work, my presentation will talk about accurate bandgap determination for bismuth manganese oxide thin film. For some years, I was using the frequently method of bandgap determination. I'd like to mention a few. The TAL method is based on the optical absorption coefficients, the spectroscopy ellipsometer, and the Beer-Lambert law. In the process of my investigation, I discovered another method that is found to be very accurate. So let's get started. Outline of this presentation is as follows. We have the introduction, the objective, materials and method, material characterization, results and discussions, finally conclusion. Introduction. Bismuth manganese has a highly distorted perovskite structure at room temperature. It also believed the crystalline in monoclinic space group C2 at room temperature with the lattice parameters as mentioned. In optical characterization, the general and most widely used procedure to determine the band gap over decades has been the TAL plot method or the reflectance versus photo energy plot. But today, we will look at another method of determining the band gap. Bismuth manganese oxide, it found its potential in optical sensors, photovoltaic devices, magneto-electron-based devices, and non-volatile data storage memory. Objectives: to determine the bandgap of bismuth manganese oxide thin film using the valence electron energy loss spectroscopy by transmission electron microscopy VEELS technique. To grow bismuth manganese oxide on 0.1% of niobium-doped SrTiO3 100 single-crystalline substrate using radiofrequency magnetron sputtering method. Finally, to study the structure and the optical properties of bismuth manganese oxide thin film. In materials and method, we have that the sputtering chamber was evacuated to the base pressure of 5 times 10 raised to power minus 10 torr, and the radio frequency R was 60 watts. Deposition temperature was 600, and high-resolution transmission electron microscopy sample of bismuth manganese film we use for the VEELS analysis, and we prepare in a focused ion beam. In consideration to eliminate the plural scattering from VEELS, energy loss to be separated more efficiently, this was used for the optimization analysis. We have pi square, and here we have the Boy's radius, electron race mass, speed of incident electron, the number of atoms per unit volume, where this is the characteristic scattering angle for a particular energy loss. We have here the complex dielectric function at energy loss E and momentum transfer. Additionally, the single scattering distribution we obtain using the digital micrograph data, we are being represented in equation 1 here. Material characterization, this way the different techniques used. Results and discussion. The high-resolution transmission electron microscopy technique was required to complement the structural characteristic and the integrity of the interface of bismuth manganese oxide at nanometer resolution. Is the representative sample of the cross-section of the film. bismuth manganese oxide film. We have here showing the thin film, and here is the substrate scrotron titanic oxide with 113 nanometers. The interface between the film and the substrate is well defined without no appreciable interdiffusion between the film and the substrate. From this micrograph, the film thickness was determined to be approximately 110 nanometers. 3B here shows the interface of the nanocrystal represented with a white square region. An interplanar distance is being observed, 110, which equals to 4.75 Armstrong units, and 201, which equals 3.55 Armstrong units of the thin film, while 100 is of the substrate. This plane and their respective indexing is according to the XRD class, which is monoclinic bismuth manganese oxide structure with space group C2. From here, the crystalline are randomly oriented with respect to each other, which demonstrate the polycrystalline nature of the film, with no indication of epitaxial layer form. Here is the fast Fourier transform pattern in accordance with the max square here. Using the polynomial fits from this equation, where A and C is constant, the fittings was obtained for the band gap to be 1.63 electron volts. In 4B, we have the conventional tau plot method for estimation of the band gap from UV via spectroscopy data, and was found to yield the band gap, which is equivalent to 1.63. From here, we can conclude that bismuth manganese oxide thin film were obtained via radio frequency magnetron sputtering technique followed by a high temperature ex situ thermal treatment. Two methods were used to determine the band gap for bismuth manganese oxide thin film. Conventional tau plot method for estimation of the band gap from UV via spectroscopy data was found to yield band gap value of 1.63 electron volts, which is equivalent to the obtained results from the VEELS technique. This suggests that one can conveniently use the VEELS technique in place of the tau plot for accurate optical bandgap determination for all semiconductors.
Thank you for your time. The authors acknowledge the support of panelists and thank the members of staff at the Center for Research in Advanced Materials Science, CMAP. I will be glad to answer all your questions.